Hello world, my name is Israel. In this video we will talk about the difference between homomorphism in algebra and homeomorphism in topology. So, in the case of homomorphism, there are three terms which are different but similar here: isomorphism, homomorphism, and endomorphism. Suppose that E and E' are magmas, i.e. sets endowed with laws of composition. We will denote the distinct laws of composition by the same symbol, T. Conforming with the general definitions, a bijective mapping f of E onto E' such that f of xt' equals f of xt f of y for every ordered pair xy of E cross E is called an isomorphism of E onto E'. A mapping f of E into E' such that the relation one holds for every ordered pair xy and E cross E is called a homomorphism or morphism of E into E'. If E equals E', f is called an endomorphism of E. So we have this general relation 1, which characterizes an isomorphism in the case where the mapping f is a bijection. It is called a homomorphism in the case where the mapping is arbitrary and merely satisfies the relation, and it's called an endomorphism in the case where E and E' are the same. Now for homeomorphism, first some examples of topologies. Given a set X, a topology is a particular collection of subsets which satisfies axioms O1 and O2. There is a minimal topology in the sense and a maximal topology. The minimal topology is the set consisting merely of X and the empty set, and the maximal topology is the set consisting of all subsets. The latter is called the discrete topology on X, and the set X with the topology is called a discrete space. So a homeomorphism of a topological space X onto a topological space X' is an isomorphism of the topological structure of X onto that of X'. That is to say, in accordance with the general definitions, a bijection of X onto X', which transforms a set of open subsets of X into the set of open subsets of X'. X and X' are said to be homeomorphic as if there is a homeomorphism of X onto X'. Example, if X and X' are discrete spaces, any bijection of X onto X' is a homeomorphism. And a useful criterion: for a bijection f of a topological space X onto a topological space X' to be a homeomorphism, it is necessary and sufficient that the image under f of each open set in X is an open set in X', and that the inverse image under f of each open set in X' is an open set in X. Interesting. Okay, so subcontrary sections and conics. So we will show that if a section HK is drawn subcontrary to a conic section ABC, then the section HK is a circle. So first we define what we mean by a subcontrary section HK. We suppose that ABC is an axial triangle, i.e. that BC is a diameter, and that the axial triangle, its plane, passes through the apex A and the diameter BC. We further suppose that the plane of ABC is perpendicular to the plane of the circle BC. Again, we suppose that the section HK is defined with respect to a plane HK, which is perpendicular to the plane of ABC. Again, we suppose that the line of intersection HK between the plane of the section HK and the plane of ABC produces a triangle AKH. No. Produces a triangle AKH, such that the triangle AKH is similar to the triangle ABC. Intuitively here, the triangle ABC and the triangle AKH are the same, up to a scaling and a rotation. These conditions determine a section which is called subcontrary. To show that the section is a circle, choose a point P arbitrarily on the section HK. Choose a point F arbitrarily on the circle BC. Draw a line PM perpendicular to the plane of ABC. Draw a line FL perpendicular to the plane of ABC. Because of the way we constructed these planes as being orthogonal, the point M that lies on the plane ABC will also fall on the line HK, and the point L which falls on the plane ABC will also fall on the line BC. Again, PM and FL are orthogonal to the plane of ABC by definition, hence they are parallel to each other. Construct a line DE passing through M and falling on the sides of the triangle ABC. Then we have two pairs of lines, PMDE and FLBC, where PM is parallel to FL and DE is parallel to BC. Hence the plane passing through DE and PM is parallel to the plane passing through BC and FL. Hence the square on PM is equal to the rectangle DMME. Here, this uses the Pythagorean theorem in an interesting way. So, there's, suppose we have a circle with diameter DE and point P lying on the circle, and orthogonal from P to M. Then the triangle DPE is always a right triangle. This is proved in Euclid. And furthermore, the line PM deconstructs this triangle into two similar triangles. And observing the similarity, we have this interesting algebraic equivalence. So we have the standard Pythagorean theorem and this algebraic decomposition and simplification. It tells us that the square on PM is equal to the rectangle DMME. But it goes both directions. It's an equivalent statement. So we have the square on PM is equal to the rectangle DMME. So there's a really clever argument here. So by our hypotheses, the triangle HDM is similar to the triangle EKM, because both the angle AKH and the angle ABC are equal to the angle HDM, and the angles at M lie opposite, so the angles must be the same, so the triangles must be similar. Hence the ratio of HM to DM is equal to the ratio of EM to KM. Hence the rectangle HMMK is equal to the rectangle DMME. But the rectangle DMME is the square on PM. Hence the rectangle HMMK is the square on PM. And P was chosen arbitrarily. Hence the square on PM is always equal to the rectangle HMMK. That is to say, this algebraic characterization always holds. But this is just the characterization of a circle. Hence every section drawn subcontrary is a circle.